This video I hope to touch on the plastic stress strain equation, or your constitutive anyway, some equation is constitutes or constitutive equations, just like your stress is equals to your Young modulus times your strain. Alright, so this whole thing over here is equivalent to somewhat like this, but it's totally not there. Alright, but similar concepts apply. So we're gonna use some exercises to see how is this being applied, and then we'll check it out with things. Alright, and therefore let's start. So if an equivalent plastic strain increment is this thing over here, alright, 0.003, and take note is equivalent, and therefore is d absolute EQ, occurs in the material subject to a stress, tada. Alright, so determine the plastic strain increments, tada. So based on this equation, this is the one that we want to find. Alright, it's 3.2 times your equivalent divided by your warmnesses times your devolteric stress. Alright, so same equation can be seen within this system. Alright, this is the one that you want to find, 3/2, and then your equivalent, your warmnesses, and your devolteric stress. Okay, so we'll first start off with finding your warmnesses. If you still remember the warmnesses, he keep using this equation over here is your J2, alright, or your 3 times J2 plus your 3ky, if you still remember the shear part of your U strength. Okay, but anyway, you eventually go through with you, so it's eventually you'll calculate in terms of this thing. Alright, where your sigma is equals to this thing over here. Take note that you're gonna bring the square root over to the other side after you calculate finish. Alright, the next thing you're gonna calculate is your hydrostatic stress, where this is talking about taking this value, add them up together, divided by 3. Alright, which is what we are doing. 400 plus 100 plus minus 100. So it's just for you to see lah. Alright, just compare only. 400, 100 and minus 200. So it's over here. Just take note of it. Okay, so it's equals to 100 MPa. Alright, so the hydrostatic stress is that. Alright, and if you remember, your devolteric stress is taking your stress tensor, this thing over here, and minus your hydrostatic stress, and what we have is this thing over here. Alright, so we are just simply finding stuff and then just sub it in only. And then this value is given, your equivalent incremental, which is over here, 0.003. And then you just sub in your warmnesses we have found already, 647, and then you just sub in your devolteric stress, which is your pure shear system. You get this thing, and this thing over here is your we call this the strain increment in all these stresses. Alright, as you can see, you'll get, we are somewhat showing the strains in all the directions of your cube, of your body. Alright, so at all directions you have certain strains, and this is being shown over here. Alright, 6.955 times 10 to the negative 6, and multiply with your devolteric stress, and you'll get some strain increment. So I can't visualize this because it's in terms of 9 components. Alright, these are all 9 values. But however, you should know that at all of the values over there will be a certain strain increment somewhere. Alright, the shape may be a bit deformed, things like that. Alright. Next question is that in a uni-axial tensile test, meaning you're gonna have some object over here, and then you just pull it in one direction. This is called a uni-axial. And that the ductile steel initially used at 350 MPa, and then hardens linearly until the stress is 750 MPa at a strain of 80%. Alright, so therefore sketch a stress strain curve to describe the 3D response of the material, and if it deforms according to your J2 flow theory, or the equation that we use in what we have calculated over here. This is some of the J2 flow theory or equations that we will be using. The same thing that will be done just now, alright? So state clearly what each axis represents. Wow. Alright, so how do we start? If you still remember your stress strain curve, this part is linear, and up to your yield strength, alright, it starts to go unlinear. I mean non-linear, sorry. So this part is your linear part, and then this part is your plasticity part. Alright, it starts to deform permanently, so to speak. Alright, and this is your stress strain curve, your strain and your stress over here. And then if I were to crop out this part over here, if I were to zoom all the way out over here, I'll have something like this. Okay, my maximum is my von Mises, and this part is my yield stress at this point, which is equivalent to this point over here, and then my strain. Alright, so we say that initially it yields at 350, so this point over here is 350 MPa, and then it thereafter hardens linearly. So sui lah, is linearly, so it's just 750. Alright, it reaches at stress 750. So therefore at a strain of 80%, okay, so we know that it's somewhat 0.8 strain. Okay, let's see how it goes. Alright, and therefore how do we do? The first thing we need to do is to find our von Mises stress first, right, before it yields. And therefore I believe you really know how to use this. Alright, this is somewhat you can say that it's a J2 flow theory in fact this is J2 flow theory lah. That's not I say wrongly. And the Prandtl Rius flow rule, whatever, I don't know what the hell, but yeah, it's this one. I don't know, just check it out. But still, you have to first find your von Mises stress first, and then you get your equivalent, your strain equivalent first, your equivalent plastic strain. Alright, which is the value, this one, this thing over here. Okay, so you can calculate the equivalent equivalent plastic strain as taking sigma m minus your yield strength, all divided by your so-called your input stress minus away your yield strength. Okay, so it's a ratio between when it yields, and the ratio between any yields and the stress that you put in. Alright, so when it yields is 520 because it's a von Mises stuff. Alright, and minus your yielding part, and then 750 is actually the stress that you put in, 750. But you may wonder, why is my 750 it should be over here, it should be over this region, it shouldn't be below sigma m, because since this is 50 20, 520 I think, is it 520? Yeah, 520. So yes, and therefore it's not this system is not a pure yielding. It's an assumption such that it is due to the normal stresses that is way too big, that it causes hardening, that your material yields with a larger so-called strengths, or you require certain hardest stress. This can be, go back to your this criteria over here, if you still remember. This is the one that if you reaches your yield strength somewhere over here. Alright, if you're within this thing, you are considered safe. Alright, and if you were to pull, alright, if you were to extend this thing over here just at this direction, sigma 1 for example, the tensile one, you're gonna further increase, you're gonna cause strain hardening, and this boundary layer over here, this criteria will also increase over here. So you'll require more stress to further pull it until you fracture. And the more stress you pull it, the more you're going into, instead of the yield stress, you're talking about instead of the ultimate stress. Okay, it can be reflected over here. Alright, so this phenomenon occur when you start to pull and the things and your material starts to harden, and you may require more stress to pull it, alright, to eventually make it fracture. Alright, so your yield stress is here, your ultimate stress is here. Alright, so you're gonna have a lot of strain hardening to actually do some work to it. Alright, but just to let you know about it. Alright, so therefore the ratio, and multiply by 0.8. Alright, 0.8 is your you have at a strain of 80%. Alright, so this thing over here causes a strain. Alright, however, due to certain reason, this strain has to be times 0.8. Alright, due to maybe experimental results stating that the accurate one should be 0.8 times your ratio instead of 1 times your strain itself. Alright, therefore this is just some percentage factor that you can multiply inside your strain, and it's something new, and therefore you may need to consider. And our purpose is in fact just to find this one, your equivalent plastic strain, or in other words, this thing over here, which in the previous part of our video where actually is given, right? If you just take a look, we are given, it states that this one is equals to 0.002. Alright, in case we calculate ourselves as 0.34, then you can simply find your own hydrostatic stress again, and then find your devolteric stress again, and then just sub in all the stuff also. You know your sigma m, you know your equivalent already, you just sub it in, you'll get this thing over here. And therefore this is just your incremental strain, or your plastic incremental strain at all the directions. So at all directions of the particular body, you have different strains that is going on. Alright, things like that. Last one is that a steel billet, when you see a steel billet, this means that it's a long piece of metal over here. We're going to assume that it's a plane strain assumption. Alright, so you're just going to talk about 2D now. Alright, with sides of length 1/3. So we have 1/3, 1/3 over here. Alright, is to be reduced in forging, pressed by uni-axial compression, and the press can be developed blah 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 with 10,000 tons, and then write down a stress tensor, determine the devolteric stress and mesa stress. Something familiar to you already, right? If you still remember, for a 2D system, alright, the sigma 1 and sigma 2, 0, 0, alright, this is for, the largest value is for tensile, the smallest value is for the compressive. And therefore, since we already know that this is a compressive system, uni-axial compression, we're going to talk about just sigma 2. Alright, and stress itself is talking about the force divided by your area, perpendicular area. Alright, so your force is given as 10,000 times, it's actually 100 meganewton. Alright, you just times, is it 10? Okay, sorry. Ton means 1,000. 1 ton is 1,000 kg. Alright, and then times the gravity 10. Alright, so this is 1 ton, and then this is the what we call the gravity. After which you have 100 meganewton. Alright, and then since we know that the billet, as we have identified, is 1/3 by 1/3. Alright, so therefore the area itself is just 1/3 square, or 1/3 times 1/3. You have 19. Alright, meter square. So force, this 100 meganewton divided by 19, you'll get 900 megapascal. Alright, negative is because it's compressive, so therefore this thing over here. Then you can sub it in as your 2D. Alright, but because they want you to actually write down the stress tensor and determine the devolteric stress and things like that. So it will be best if you write things in terms of a 3D for safety's sake. So therefore we write in terms of a 3D, where the minus 900 is at the middle, where the rest are all zeros. This is 0, 0, 0. Alright? And then your hydrostatic stress is simply 1/3 times your whatever sigma 1, 1 plus sigma 2, 2, things like that. Eventually this thing plus this thing plus this thing divided by 3 is minus 300. Alright, so after which you take this, your stress tensor, minus away your hydrostatic stress, which is minus 300, minus 300 and minus 300 over here. So minus 900 minus 300, 80, minus 300 is 300 over here, and then minus 900, alright, minus 300 is minus 600, because minus 900 plus, minus is plus. Therefore, I think you get what I mean already. Alright, so therefore what you have seen here is your devolteric stress, just simply something about your shearing system, but instead it is still talking about normal system still, or in the normal to whatever plane that is. Alright, all the 3 planes, normal to the planes, so to speak. Alright, a billet is uni-axial compression, meaning only in terms of sigma 2, 2, then you can straight away sub in your von Mises as a 900. Otherwise, you can also sub in into your your equation, your von Mises equation, alright, this is totally not the values. Somewhat don't care, rather than just care about subbing in into this equation. When you sub in into this equation, you're subbing in as sigma 2 and sigma 2 over here, the rest as 0. Eventually, you'll still get 900. Okay? And therefore, this is your von Mises stress. And now, therefore, we're going to calculate our equivalent. You still remember the equivalent incremental strain. Therefore, talks about the part B. Alright, it states that the material initially used at minus 750 MPa and then hardens linearly before fracturing at the stress of minus 100 MPa. Because it's talking about why minus is because you're compressing. Alright, compressive. And a plastic strain of 100%. Alright, so it's cool. Alright, so sketch and label the graph of your misses and things like that. Alright. Okay, so let's continue. Alright, so if you want to calculate your equivalent, or your equivalent incremental, it's taking your von misses minus away your U stress, and then divided by your input stress minus away your this thing over here, your U strength. Alright, multiply by your strain percentage. Alright, in this case it's 100%, so it's times 1. Alright, so therefore the ratio between your von misses and your input stress will somehow give you the equivalent strain. Alright, so therefore if you were to input there, get that. Alright, so this, if you just keen, just to show you this, this is the von misses. Alright, actually sorry, this is the U stress. It's because initially where is initially? Initially it yields at 750 MPa. Alright, minus 750, but it's still the same. So, and then your input stress is 1000. Alright, while your von misses is somewhere 900. Alright, so this thing over here is somewhere about 0.6. Alright, this is somewhat of the ratio you're talking about it. Alright, therefore, let's sub it in now. You just simply sub it in, and the rest, I think you should know your divideric stress tensor, which you have found earlier. So subbing your von misses, your these things, you eventually find your so-called the plastic, alright, plastic incremental strain. So this means that this strain over here means that the strain changes across your body again, alright. And how does the body change? Things like that, alright. It may deform to whatever extent that is. Okay. So the takeaway is to know this graph, how to use this graph to find your equivalent incremental strain, and take note of the percentage. Alright, the percentage. Alright, if it's 0.8 or 1%, take note of the language they use. Alright, like the plastic strain 100% or 80%, things like that, and take note of the linearly the word and things like that. Alright, and you should be fine, because the rest is just simply subbing in the equation and you're the king. Alright, I shall see you in the next video for other stuff. Goodbye.